So the drift of moving charges through a conductor can be interpreted in terms of work and energy. The electric field E does work on the moving charges, and the resulting kinetic energy is transferred to the material of the conductor by means of collision with the positive ions, and these ions vibrate about their equilibrium position in the crystalline structure of the conductor. So this energy transfer increases the average vibrational energy of the ions, and hence the temperature of the material increases. So the work done by the electric field goes into heating of the conductor instead of making the movement of charge faster and faster. So this heating is like an unavoidable byproduct of current flow. Sometimes it is useful, for example in electric toaster or in furnaces. So in different current carrying materials, charges of the moving particles, this movement of the charged particles uh, maybe because of electrons, or maybe because of electrons and positively charged ions, or sometimes in materials like semiconductors, uh, the conduction is partly by electrons and partly by the motion of vacancies, also known as holes. So here this figure shows segments of two different current carrying materials. Here the moving charges are positive. The electric force is in the same direction as the direction of electric field, and the drift velocity is from left towards right. The changes here in this one, the charges are negative. The electric force is opposite to electric field, and then the drift velocity is from right towards left. In both cases, here and here, there is a net flow of positive charges from left to right, and positive charge end up from left to right, and positive charges end toward the right of negative ones. For the current, we define that this is a flow of positive charge. Sometimes the flow of in actual, the current flow is due to electrons, but due to convention we say that this is due to motion of positive charge, and this current flow is called conventional current. So the direction of the conventional current is not necessarily the same as the direction in which the charged particles are actually moving. Now let's move to this figure here. This figure shows a battery and conductor in which the charge is flowing, and this is the segment of a conductor here. The moving charges are here positive, and they are moving in the direction of the electric field. So it means they are moving the same direction as the current. So we define the current here in this case through the cross sectional area to be the net charge flow through the area per unit time. Thus, if a net charge dq flows through an area in a time dt, the current I through the area becomes I is equal to dq over dt. Current is not a vector, it is a scalar quantity. For example, in a current carrying wire, the current is always along the length of the wire, so regardless of whether the wire is a straight or curved. And when we consider vector, a single vector cannot describe the motion of a charge along a curved path, so that's why current is not a vector. For the to give a direction direction to the current in a circuit, you choose either the flow either is a clockwise or it is a anti-clockwise. The unit of current is ampere. And is defined to be 1 coulomb per second, and this unit is named in the honor of French scientist Andre Marie Ampere. So let's go to the next video and discuss drift velocity and current density there.